This is the 46th lecture in a series on single agent search, and today we're going to be talking about compressed path databases. And compressed path databases are something that's related to storing all pair shortest path data, as we'll see in just a minute. But there's actually an interesting intersection that they have between looking at the difference between heuristics and constraints. And so if we think about all pair shortest path data, one thing we might typically be storing is just the distance from any one state to any other state, or the distance between any two states. And so as that would be all pair shortest path data. It could take two forms, right? So we could have that in terms of distances between states. And if we do that, then that's essentially a heuristic, right? Because when we're storing and estimating distances, then we have heuristics. But there's another alternative that we could use, which is somewhat different than this. We could also be, if we're storing distance between states, we could also store basically the paths between the states. Now, if we store actually the entire path, then the overhead is going to be very large. But generally speaking, if I store the first action in a path, then I'm going to be taken to a new state, and from that state, I'll also know the first action. So we could continue from that. So if we're storing path information, first step path information, then this is essentially a constraint. Because now what we're saying is, instead of saying that this is the distance between two states, what we're saying is that you should constrain your search to only generate this particular successor. Okay. So when we look at the all pair shortest path data, we could interpret it in two different ways. We could interpret it as a distance, or we could interpret it as a constraint. And if we look at something like differential heuristics, what they're trying to do, especially as we're building up many of them, those can be viewed as a compression of the all pair shortest path numerical data. And compressed path databases are then a technique that's been developed. There's been quite a few papers published on it that are saying, let's look at this as a constraint data, constraining where the path can go, and then ask the question, now how can we do pathfinding with this? And so I think it's valuable to look at both of these paradigms to understand how these paradigms work together and understand what they offer as we look at it in two different ways. And so the original paper was developed by, there's a journal paper by Ben Strasser, Adi Botia, and Daniel Harbour in 2015. It also has some nice theoretical results in there about the difficulty of doing the compression and doing some of the optimization. But in this lecture, this video, I'm going to basically give an overview of what the compressed path databases are, and then we'll look at some of the techniques that have been developed, both in that paper and later papers, to give us a sense of what can be done. But as I said, there's a number of other papers that we're not going to cover in detail here. And to start out, we're going to use an example that comes from their paper. And so I'm going to start out by, sorry about that, we're going to start out by drawing the all pair shortest path data. And we're going to draw a graph. We're going to look at what the data looks like, and we're going to talk about how we could be looking at that data and what can we do with it to be able to compress it. Okay. So we're going to have a simple example here, a simple graph. And what we're going to do is, so I'm going to number these. I'm going to number each of the states. And then I'm also going to be numbering the edges. So this is 4 and this is 5. Okay, so here we have a simple graph. And let's go ahead and label the edges. So this is label edge A. This is edge B. We're going to do edge C over here. Edge D is going to be down here. Edge E is going to be over here. And edge F is going to be over here. And then associated with each of those is going to be a cost. So A has cost 2, B has cost 5, E has cost 3, C has cost 3, D has cost 6, and F has cost 4. And then what we can sit down and do and say, well, if I had this data, what would an all-pair shortest path look like? And so here we're going to look at ST paths. Now, this is an undirected graph, so this doesn't, we don't have to worry too much about the undirected nature, but we can be thinking about ST path, and we can think about our nodes, which we've numbered 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. And then we can ask the question, what is the first action you would take if I want to go from S, so we want to go from 1 to T, so let's say from 1 to 1. So from 1 to 1, there's nothing we want to do there, so in fact the diagonals are going to be empty. And now we can start thinking, well, what happens if I want to go from 1 until 2? So here's node 1, here's node 2, and the shortest path here is to go straight across. So that's going to say take action A. What if I want to go from 1 to 3? Well, it ends up that there's actually two possibilities, right? This path is cost 5, and this path is cost 5. And we could do either of those, but we might have some tie breaking that tells us it's a little bit better in terms of the compression we're going to want to do to try and take the same move all the time. So if I can take the same action here, I'll prefer to do that. The next thing I want to think about is how to get to 4, which is over here. So this edge here would be these two edges would be cost 11. And so the shortest path is going to become this way, which means the first step on that path is going to be to take A. And when we're thinking about getting to node 5 right here, again, we know to get to 3 that we can go either way, but let's take A first and then go to C, in which case A is always going to be, again, is going to be the first action we want to take. And the next thing we could do, let's just look at the next row here. We'll continue looking at these rows. So now I'm going from 2 to somewhere else. So here we're going to say we're going to take action A to get here. We're not going to take any action to go from 2 to 2. And then we can say for going from 2 to 3, this is cost 3, so we're going to want to take action E there. Going to EF, so node number 4. And so what we see here is this is cost 9, this is cost 4. So we'll want to take action F there. And then if we're going to node number 5 here, then we're going to want to go straight across here. So that's going to be back to action E. And thinking about node 3, if we want to go to 1, so again, we'll use the same thing in the backwards direction. What we're going to say is take E to go here. If we want to go to 2, we'll also take E. If we want to go to 3, we don't need to think about that. And then if I want to go to 4, then I'm going to take D, and if I'm going to go to 5, I'm going to take C. So what we're going to get here is E, E, an X, a D, and then a C. And when we're thinking about node 4, so node 4, if we're trying to go to A, then we're going to take F. Node 2, we're going to take F. Node 3, now this is 7, so we're going to go take node D, which would be cheaper, would be 6. So that's 1, 2, 3. Node 4, we don't care, and node 5, we're also going to take D. So what we get here is we get FF, D, X, D. And for node 5, because node 5 is out here on its own, we're always going to start out by taking C. Okay, so this gives us an entire example. And what we're going to think about is run length encoding. So what is a run length encoding? Run length encoding is going to say something like, if I have a symbols like A, B, 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 A, then what we're going to say is, and we'll number these. So this is index 1, 2, 3, 4, 5, 6, 7, 8. We're going to encode this by saying start taking, so my first thing is going to say start taking ones, or sorry, at location 1, start taking A. At location 3, start taking action B. And at location 6, start taking location A again. Or sorry, at location 6, start taking action A again. And so, like depending on the size of your symbol sets here, we've needed 1, 2, 3, 4, 5, 6. And here we had 8 total. So we've reduced the number of symbols that we need to store this encoding here. Now, if we wanted to have an encoding that wraps around, we could allow the coding to wrap around, in which case you could say something like start 3 at B, and then we could say, start A at location 6. And then if we're trying to look for the 1 here, what happens at location 1? What we'd actually know is it's going to be the last symbol, not the first symbol. And so we could actually do this even more compactly using 4 symbols. And so this would give us a 50% compression of this string. So the idea of run length encoding is basically we're going to look for runs of the same symbol, and we're going to encode the starting location followed by the symbol. Okay. And so if we use this and we go back to the data that we had before, so let me, I'm just going to move these slightly out of the way here. Move that over. Move this up. Now we can store the run length encoding here. And what we're going to want to store is basically what we should be doing for 1, 2, 3, 4, and 5. And what we're going to do is we're going to store these rows as a single run that's compressed together here. And so what we notice here is that this X, we don't have to say what the X is. Of course, this is always going to be nothing, but we can treat this as any symbol that we want. It could be the same as the symbol before, the symbol after. So here we're going to say, using our encoding of before, we're going to say starting at location 1. So this is 1, not 0 based. Then we're going to encode an A here. And this is all we need to say. If I want to look up what encoding is, basically I can search through this representation to try to find where where my symbol starts. And here there's only one thing, 1A, there's nothing after that. So now I know that everything in this row is going to be A. The next one is a little bit more difficult. So what I'm going to say here is I start out with an A, so 1A. And the X we don't really need to encode. So what we're going to say is at location 3, we're going to start with E. And then at 4, we're going to have an F. And then at location 5, we're going to go back to an E. Okay, so that's not particularly an efficient way to encode that row, but other rows will get better encoding on. So if we go to row number 3, then what we see here is at location 1, we're going to start with an E. And just to show this, so right here, we're starting with an E. And then we're going to have the D and the C. So at location 1, we have an E. At location 4, we have a D. At location 5, we have a C. And for the 4th row, we get a little bit better here. So at location 1, we're going to have an F. And at location 3, we're going to have a D. And that's going to give us all of the D plus the X there. Because this symbol doesn't really matter. When we're going from 4 to 4, then we know that we're already there. And last thing we see is this last row can be stored as just 1C. Because we're always going to use the C as our first action there. And the idea here is that if we can build this all pair shortest path data, and in this case, we do have to build the all pair shortest path data. So I'll come back at the very end of the lecture and say something more about that. But let me point out here, if you're wanting to do something like this, running canonical Dijkstra, if you're on a grid map, allows you to build this all pair shortest path data significantly faster than if you were just trying to run a straight Dijkstra's algorithm to do all pair shortest path data. So, this is just a place where if we were on a grid map, we might want to use a more efficient algorithm to compute this, but it's still going to be a little bit expensive. We're going to have to do this and compute this and store it, although we could do some of it incrementally. And when we do that, then we're going to compress this and we're going to convert it into this representation, which we can then use. And so what we're trading off here is we have a reduction in the space that's used to store this table. But the trade-off for that reduction in space is that it takes a little bit more time. If I want to look up, if I'm at 3 and I'm wanting to go to 5, then it's going to take some time for me to actually go through this table and figure out where's the action that I get there. Okay, so by doing compression, we're trading off space for time. And so that's what this gives us here. And the next thing we want to look at is some of the parameters we have here. So if you looked at right here, what we've done is we've just put some arbitrary ordering, 1, 2, 3, 4, 5. We have some costs here, and we just run with that, and that gives us our values. But it ends up that we can think about what ordering do we want to order our nodes, and by changing the order of our nodes, we can actually change the efficiency of how we run. And so what I'm going to do here is if we can just take this example that we have before, and we can duplicate it, and all we're going to do here is go into this example and change the ordering of these nodes. So you can see the ordering we had from up above, and now we're going to change the ordering and say 1, 2, 3, 4, 5. And let's look at what the impact of this does. So I'm going to do this a little bit faster than I did last time. But again, we have an ST, so S is the source, T is our target. If I'm going from 1, then the same thing as before. Anywhere that I'd want to go in the world, I'm always going to start out by going to 2, and so I'm always going to have that A action. So not much different there. We're going to get an X and then an A. Okay. But if we look at our next row, then it's going to be a little bit different because now 2 is over here. And so we're going to start out by going to A. To get to 3, we're going to go to F. And then to get to 4 or 5, we're both going to go to on action E. So what you see right here is we had A and then E and then F and then E. But by changing this order, we're going to get A as we had before, and our X as we had before. But now we're going to get F, E, E. Okay, because from 2, 4 and 5, which have the same prefix, are going to come together, and they're going to come after the 3. So we get better compression in that row. And if we look at number 4, what we're going to get in the third row. So from the third row, we're going to, for 1, we're going to go up here. For 2, we're going to go up here. So we get those actions being the same, which is the same thing we saw here. And but we will see is that for actions 4 and 5 now, 3, so up here 3 was 4. So we saw these 2 actions being the same, and then we're going to see these 2 actions are the same. So that is basically the same for row 3, but it's been renumbered. So we're going to get FF, X, and then DD. And for what is 4 down here, so before 4 was this one, it's 3, but now 4 is the middle one here. So let's look at what happened here. We got EEXDC, and in our new ordering, what we're going to get is actually something very similar. So we're going to get EEDXC. So not much difference there, and you can see that we can't do much better because really we have to head, from here we always have to head this way to get to these 2. We have to go a different direction to get down here and a different direction to go there. So we can't really avoid that. And for our last one is still 5, we're going to get CCCCX. Okay, so the only difference that we see here really is in this second row. We've arranged these E's to be next to each other. Instead of having the F in the middle, now the 2 E's are next to each other. So the run length encoding, I won't take the time to write them down, but it's going to be slightly reduced because I've managed to get these next to each other. So the question then we would ask is, how am I going to actually do this, and how hard is it? So the paper here discusses the complexity that is NP hard to try and do this. And I believe it's NP hard. It could be NP complete. I'd have to go back and look at the paper to double check that. But if we look here, the question is, well, how do I actually do this in practice? And this actually shows us here, this process we've gone through is actually shown us some insight here. And what we've seen is that by having the 3 and then the 4 and then the 5, the 3 actually leads us to the 5. It leads us to the 4 and to the 5, but the 4 is sort of a different direction, and it's a different part of the graph. Where here, the 4 and the 5, you have to go through the 4 to get to the 5, so it makes sense to have those in order. And so what this suggests is how you could build these compressed path databases, or how you could build these orderings, would be basically to do a depth-first search. If we do a depth-first search through this tree, and depending on how I do this, so I might come here, I might come here, and then at this point, if I go down here, then I'm going to end up that I will get these orderings together. I could come this way, and that might work well. Of course, I could do a depth-first search and go this way and this way and then this way. And so there's still some tie-breaking issues that would occur in a depth-first search. But generally speaking, we could use a depth-first search as a way of ordering this tree, ordering the numbers that we get here, and trying to ensure that we get the best possible compression here. Okay, so this is the first step that we could do. And this is, overall, this was called single row compression. And we can have another technique that basically says, hey, look, then when we look at some of the examples that we have, we can actually encode them more efficiently. But as we can notice that there are some sequences that are common, or some values that are common between the different rows here. And so in particular, so let's actually go ahead and write down what would the compression be for this table, the one that I didn't write down before. So 1, 2, 3, 4, 5. And so what this would be is 1A. And then here we'd also have 1A followed by 3F and 4E. How did I do that? 4E. And in the next one, we get 1F followed by 3D. In the next row, we see 1E followed by 3D and followed by 4C. And in the final row, we see 1C. And what we can notice here is basically that on these rows here, we can see that there's some overlap. So in particular here, we can see that there's a 1A both here and both here. The other thing that we can see is that there is a 3D that occurs both here and both here. And if we wanted to, we could notice that there's a 1C here. There's not a ton of value in compressing this. But what we can say is basically we can say, I'm going to assign a label. So let's assign a label here. For instance, X is going to be equal to 1A. I can say Y is going to be equal to 3D. And I can say Z is equal to 1C. And now when I go to encode, I can encode these rows together. And so when we're thinking about these rows, we can say that we're going to represent them. So I'm going to write these 1, 2, 3, 4, 5. We can now say, well, there's some common symbols here. And so row 1 is just an X. Row 2 has an X in it, but then it also has a 3F and a 4E. Row 3 has a Y in it, followed by, so let's look at row 3. Row 3, so what has a Y in it, which is 3D. 3D is this piece here. And so we're going to have to also encode the 1F. And so I have to be a little bit careful here. It's not followed by a 1F, but it's a 1F and it also has a Y inside it. Similarly, we also see a Y inside here. and then we'd see a 1e and a 4c. And finally, if we have our z here, then this is just a z. So we can not only be looking at rows across here, and we can be seeing that there are often patterns here of what we need to do, of the actions that we need to take when we're going to various different goals. We can also look here and see that between rows that we can have commonalities between rows. And when we see common pieces between rows, then we can compress these different rows using the same symbols here, the same table, to try to reduce what is going on in that space. Okay, so that's giving us our basic version of, well, up here is basically our basic version, and here we can get our multi-row compression. And on this basic idea, basically what you'll see is that there's a number of different papers that have been written. Some sets of papers are saying, how can we use the data? And some sets of papers are saying, how can we continue to compress the data? So I'm going to go ahead and show a couple of other ideas that are coming from, I'll show some ideas that come from a 2019 ICAPS paper by Chiari et al. Some of the same authors here, but some new authors as well. And I'm just going to show an idea of wildcards. Basically, there's all sorts of different ways that we can continue to improve the idea here. And there's a number of different forms that this can take. And so we're going to start out by looking at an example where we're going to think about, in particular, although this is related to wildcards, we're going to use in particular heuristics. This is a little bit similar to what you might do when you are we're doing something like a delta heuristic, where we say, well, we've got a default heuristic, and then I'm only going to store the delta over my default heuristic. The idea here is something similar. That is, we have a compressed path database, or we're wanting to build the rows of our tables in our compressed path database. Now we want to think about, for instance, what happens if we have a heuristic, because the heuristic gives us some information. And so we want to sort of compress away anything that was that's information that isn't contained in the heuristic, because that's going to allow us to do further compression. So there's some, if you go and look at the paper, as I said, this is a paper by Chiari et al. In 2019 at the ICAPS conference. And if we look at this paper, they walk through and do a really fairly good job of walking through and showing examples and stepping through how everything works. And so I'm going to present the ideas just a little bit more abstracted from what are in that paper, but it should give us a good idea of what can be done here. So let's think about a simple map, and I'm going to be a little bit off, but in other words, that I don't have a grid here. So we'll just do our best to sort of pretend that we see this grid, and we'll fill this in. So this is an obstacle in the middle that we can't go around. And what we're thinking about is, for this example, I guess we're going to divide this here, and we'll divide this here. Good. And we have one more division up here. Okay, and so we're going to be sitting here, and this is going to be our source state. And so this is where we're going to think about all our computation from. And we're going to think about, if I'm starting at this source here, and I want to go to some location here, what is the action? So this is we're going to define this on grids here, but what is the action that I want to take from the source to go in this direction, to get here? And if you think about it, well, what is the action? We're thinking about, now in grids, we're going to have just 8 possible actions: north, south, east, west, northeast, northwest, southwest, and southeast. And so here should be fairly clear that if I'm going to, so this is the west, this is the east, This is the north, this is the south. And if I'm wanting to go to a location here, then west is going to be the direction I want to go. Okay. And so we could start to say, for instance, I could ask my heuristic, or a number of different things I could ask, but I could ask my heuristic and say, for my heuristic, if you were to want to walk to a particular state, ignoring the obstacles, what is the action that you would take by default? And so if we look at this example, actually, since I have this table nicely filled in here, let me go ahead and duplicate it because we're going to look at a couple variants of this. So we'll fill this in again in a minute. Okay, so if I want to go to basically, what is my straight line direction to get to any particular location? We could ask which direction I would go. And what we would see here is up here, I would go north. Over here, I'm going to go west. Over here, I'm going to go east. And of course, down here, I'm going to go south. Now, if we think about the cells down here, there's a couple different ways this could be done. But if we think about a heuristic sort of saying what is the step, the heuristic is generally going to, if we're thinking about an A-star search where we're tie breaking towards large G cost and lower H, then I might be able to take both this action and this action, but we're going to say, for instance, we're always going to take a diagonal action before, an action that includes a diagonal before a cardinal. So here we'd say go southwest. And let me just make this clear. For the next state here, we're asking what is the first action we take from here. The action is southwest, after which we would have another table that would tell us we need to go west. So these would be southwest because we want to start with the diagonal actions. These would be southeast because we want to start with the diagonal actions. And then because we're going to start with diagonal actions, then everything up here is going to be northeast. And everything on this side is going to be northwest. And what we're going to observe here is if we do this, then all of the actions down here in the bottom, and to make it clear, I'll color these all green. So all of these actions down here, the heuristic is actually telling me the correct action to take first. Okay. The correct action to take first for all of these actions is actually just to follow the heuristic. So if we were to look at this and try and do a run length encoding on here, what we'd see is, I'd get a couple wests, a couple easts, some southwests, a south, and a southeast. And so I would see 1, 2, 3, 4, 5 different runs down here. But in practice, I could actually convert this to a single run that says on all of these green states, what we want to do is just take my heuristic default action. So we're going to get a new symbol. In the paper, they call this H with a circle around it. But the idea is we're going to have a new symbol here which says, take the heuristic action. And so all of these will get exactly one symbol that tells us to do all of these actions. And then these ones up here, although the heuristic would tell us to do something, it's not particularly a good thing to do. And so it's not going to help us out very much. And we're going to do, we're basically just going to have to encode those actions directly. Now, we could do a little bit better than this. And there's a couple different variants that the previous authors proposed. So let's just mark these off. I'm not going to have to really change what goes on down here. So we're not going to worry about these. But the question here is, what do I think about, for instance, and if I need to get here? So if I need to get up into this corner, what I would say is, well, typically I want to go northwest. But it ends up that northwest isn't even a legal action. So I could actually say, sure, I want to get northwest up here, but since that's not a legal action from my start state down here, let's make this back yellow again. So I want to get from there, I could say, and as I said, there's some variants that depend on your cost. So we could say, for instance, look at the world, and we could just say, well, take northwest. And if you want to take northwest, but northwest is blocked, then we're going to actually use whatever we could do legally inside there. So we could sit here and look up and say, well, I want to take northwest. I can't do that to get to any of these states. I want to take northwest. The actual best action is west. And since both north and northwest are both blocked, then we know the only remaining action is west. And so that could tell us, hey, all of these actions here are, we would encode them as being west, or we can encode them as being the default action. And by default, I would just take the west action because north and northwest are both blocked. Similarly speaking, we could just actually look at all of these here and say for this quadrant right here, I'm thinking about doing something special and say, well, for this quadrant, we're going to do a different encoding. And I know for everything inside this quadrant, the first action to get to this quadrant for all states actually happens to be west. So I could say, by looking at this quadrant as a whole, normally I would want to take the northwest action, but I'm going to actually say for all of these, I want to take west. And this would be, though we could define this as a default action or, use some other mechanism basically to say that these are, I think thinking about the heuristic is probably the easiest way to think about this, but it's basically to say, look, I wanted to go north, I wanted to go west. I wanted to go northwest. I couldn't do it. West is the only action I can do. And if west is actually the action I want to get to, then this will actually handle all of these locations here. And it'll actually, for the east direction, it will similarly handle all of these here, where I'd normally want to do northeast, but now I can convert those all to being east. So just to be clear here, we can all mark these now as actions that we take the default. Okay. And the only question then is, well, what about these pieces here? I want to take north and I can't do that. But it ends up for this particular problem, if I want to go northeast or if I go northwest, both of those are legal first actions. And so typically what I would say is, but there's a number, as I said, there's a number of different things we could do here, but basically we could look here and say, well, if north isn't a legal action, but I'm allowed to take east or west, or if I have a default ordering that says, well, if you can't take north, then try east, then I could assign these something like a north action. But by looking at a default ordering, it would basically come back to saying you could use your heuristic. So my heuristic would say, well, the best, for instance, what is the best heuristic? It's either this state or this state. And both of those are correct. If I think about my neighbors, both of those are correct first states. So I am able in this example to be able to fill in these states here. Okay. So there are quite a few more details in the paper surrounding this, and they have a couple of different optimizations that I didn't show here. But the idea here basically is that we have very specific data, particularly when we go into grids. For instance, we have a very limited wildcard set action set here of the actions that we're going to take in practice. And so by being smart about that, by using additional information such as a heuristic, we're able to take and encode some of this information so that I know I can use my default movement. Again, what we're doing here is we're trading computation, because now I'm going to have to look up my heuristic. I have to do some computation to tell me which direction to go. In the paper, they don't actually always use a heuristic. Sometimes they use simpler functions so that they'd be less expensive to compute. But the basic idea is we're going to add a little bit of computation. By adding a little bit of computation, we're going to add additional redundancy in this table. And by adding this redundancy, then we're going to reduce the size of this. And so this is very much like, as I said, taking a delta heuristic, sort of subtracting out the delta heuristic. Here, what we're going to do is we're going to take out the sort of the heuristic direction. If the heuristic direction maps to what we're trying to do, then we're going to get better values here. And as I said a minute ago, though, this still requires basically building these tables. I still need the all pair shortest path data to do this. And so there is the most recent work that's been done in this line of work on this sort of search has said, look, although we can build this on these tables here, it's going to be expensive. But a couple lectures back, we were looking at contraction hierarchies. And contraction hierarchies are a way to take a graph and shrink it. In a similar way, we could, for instance, jump point search, we can just get our jump points out of that. So, for reach, we can say we just store our reach at our states where we have low reach. And we can, let me go back. Okay, so if we think about bounding boxes, And for any of these techniques, so for reach, for bounding boxes, if we're thinking in our jump point search world on grids, we could say, once I start my search, I'm always going to be sitting on jump points. So if I only do the computation for jump points and only store it for jump points, then I'm going to save, because once my search starts, I'll immediately be on jump points, and then I can store this data for a smaller subset of states in the world. Contractions are basically the generalization of how we're getting jump points. So contractions, like in contraction hierarchies, are giving us states that are more important. They're contracting out the states that are less important. And so that's something like in some other topology where we don't necessarily have a grid, we're removing out those states in the middle. We're just getting out to these important states. And as I said, we could just store reach at those states. We could just store bounding boxes at these states. And the latest work here says this. Yes, actually, we could also do the compressed path databases inside after we've done these contractions. In a contraction hierarchy, we have this graph, which is smaller. So we're going to be back to something like the original idea here. But basically, this graph here might be the result of a contraction of a larger graph. And then we can go ahead and store this data on top of that. And so, so that is able to get very good performance. So to summarize what we've been looking at in this video is the idea of taking the all-pair shortest path data. Instead of storing it as distances, which would give us heuristics, what we're going to do is we're going to store it as basically first steps, which are essentially constraints. They say you should be constrained to go in this particular direction, and all other directions we should prune away. Okay, so that gives us a constraint. And when we do that, then we get our all-pair shortest path data, but we can use a run length encoding, and depending on how we do that, we can get it more or less efficient. Here we saw even more efficient ways of being able to store that, but basically we can take our run length encodings, store them efficiently, and then get something that is much smaller than the all-pair shortest path data in practice. And then once we have that, we can use it in conjunction with other techniques like contractions or something like jump points. You could use this and only store it on jump points, and other ideas like that. But this is one of the ideas. We're sort of drawing everything together now of seeing how we can use these constraints and compress them and get something equivalent to a very strong heuristic in practice. And so we will continue actually now to look at this is sort of the end of the techniques we're going to cover here. There are other techniques we could cover. There's a number of them that are able to do very, very fast pathfinding in road networks, but we're going to move away from road networks, and we're going to look in the next lecture at pathfinding again in game maps, because game maps have a slightly different structure, and there are suboptimal abstraction and refinement techniques that are much faster there. And so we're going to go look at those and see there and talk about some of the techniques that are actually being used in the games industry today. So that will continue in the next lecture.